Good morning again. Today, I'm Zhichen again from Meta. Today, Akash and I are going to talk about how to make vector search first-class citizen inside a query engine. As you can see, this is joint work from many Meta colleagues. The short version I want to say is that we found that vector search is a relational workload hiding in plain sight. So today we are going to show you how this works. So why does this matter? The following scenario can happen to any AI team, right? You developed a very good embedding model, and you make vector search work. Then all of a sudden, someone says, okay, I need to filter by access control. I also need to join with user metadata. Then I also need to aggregate. As a result, you find yourself stitching multiple systems together, as the previous talk. Right? You have to kind of do the SQL, then you ship your data to the vector search, then you come back. This is a lot of hustle. So the fundamental gap is that faster vector search exists, but composable vector search at scale doesn't exist. So here is a kind of quick overview of the landscape. So existing systems actually force user into a very difficult trade-off. If you look at the vector databases, right, they are very scalable, they are distributed, but they don't support SQL. You cannot compose. There's also SQL extensions like pgvector. They support SQL, but they are single node, they are not scalable. There's also cloud solutions such as Google SQL, right? They start to introduce vector search, but they only support post filter. You have to build everything in the vector index. Again, if you want to composable kind of vector search, as I kind of illustrated earlier with the example, then you find yourself have to stitch together multiple systems, which is a hassle. So this is the slide I'm most excited to talk about. What we discovered is that vector search is actually a relational workload hiding in plain sight. If you want to kind of partition your vector space by similarity, it boils down to a scalar function, right, with a code book. And if you want to build an index for per partition, right, that's a group by, then followed by aggregation. If you want to kind of search inside a partition, right, it's an equi-join, right, with global top K. So if you want to introduce kind of new index type, right, it's opaque, right, it's just a parameter. You can support flat, IVF, or RabbitQ to your choice. So this analogy is a structural isomorphism. So we are going to kind of show how we take advantage of this. So this is the architecture slide. There are two pieces which are cleanly separated. If you look at the bottom left, right, the first thing is the code book. Right, imagine they are kind of cluster centroids when you kind of partition your vector space. So this tells you where your vector lives, and you just need to kind of broadcast your code book to all the workers. The second major building block we call local index. Essentially, this is searchable artifacts, right, you build for each partition. These are the heavy kind of part of the solution. Essentially, it can be fairly large. So the elegant part here is when we kind of partition the vector space into clusters, the cluster ID serves a dual purpose. It is both a similarity proxy. It is also a distribution key. So this makes a zero shuffle vector search possible. So on the slide, I also showed the steps. First is you assign your clusters, your vectors into different cluster. Right? Then you build a local index for each cluster. Then you leverage the cluster ID to co-locate the query and the candidate vectors. Then you perform local search. Then you do a global top K. So how much code do we actually have to write? We only need to kind of implement 3 Velox functions. First is assign top k. Given the code book, how do you assign each vectors to a cluster? The second function is build a local index. Given kind of a cluster, how do you build a searchable artifact? The third function we have to implement is search the index. Everything else, like partition, memory arbitration, etc., we get this for free. If you want to introduce a new index type, you just implement a subclass. So now let me show you something very interesting, right? Because of this observation, this decomposition, we get several capabilities for free. So the first kind of capability is zero shuffle execution. Right? In a naive system, when you need to do vector search, you have to kind of shuffle every query to all the kind of candidate partition. And if you imagine, right, if you have a very large table, and if you want to partition your table into many centroids, yeah, if you have to shuffle, that's terrible, right? But because we kind of partition both the query table and the candidate table use the cluster ID, right? The query becomes local. And imagine you kind of partition your cluster into 10K centroids with an mprop of 10 and 100 worker, right? Each query only need to hit 10 shots. As a result, you only search 0.1% of the corpus. And the network saving, right? If you have to shuffle everything, you have to kind of shuffle about 1.4 terabytes if you have 1 billion vectors. But today, we only need to broadcast the codebook, which is about 200 megabytes. You got 7,000x reduction in network traffic. The second consequence is a memory-bounded index. Right? If you have a large table, let's say you have 1 billion row, each with 1,000 dimension, with 32-bit for each dimension, you have 1.37 terabytes. And we employed 2 techniques. One is a new index type called RabbitQ. With RabbitQ, it gives us an over 99% recall with about 4x reduction in terms of the index size. The second technique we employ is called subclustering. So in real world, right, when you partition your table into multiple clusters, they are highly skewed. So in one of the workload, we saw that the largest cluster can be 7 million row, which is 100x the average. So the technique we employed is called a subcluster. Essentially, we break large clusters into a subcluster and cap it. As a result, we see 25x reduction in terms of index size. So the next consequence is guaranteed result under any filter. As I mentioned earlier in the example, because build index is a standard SQL aggregate, right? You can do a where clause to first filter down your data, then you build index. As a result, you basically don't lose any recall because this is a SQL decomposition. So lastly, I want to show the power of full SQL composability. Right? For many workloads, you can express most of them in a single SQL. For example, you use where clause to do the pre-filter. You build an index on the filtered data. Then you search for top K. Then you can join with the metadata. Then you can also do a group by to do aggregate. If this is with external database, right, you have to kind of ship data to the external database, then ship it back. That's a lot of hassle. You also have to deal with consistency issues. So next is about a design issue we have to wrestle with. Right? For expert users, they want to complete control of the kind of topology. They also want to control the mprop, and many parameters. But for novice user, right, they just want something they can use. So to solve this problem, we essentially support 2 levels of API. The first level is we call the primitive, which are the 3 functions I mentioned earlier. Right, the power user can do anything they want at the cost of very verbose SQL. For the novice user, we introduce a syntactic sugar we call level 2 API. Right, so you can write a very concise declarative SQL, and we leverage the optimizer to convert from level 2 to level 1. And with that, I'm going to hand this over to my colleague Akash, who is going to talk about evaluation. And,
Thanks, Zhichen. Yep. And thanks for covering the architecture and then the consequences as well. Yep. I think we'll go over the evaluation next. So starting from the proof, we actually tested the scalability on 2 different benchmarks. One was 700 million corpus and another one was 1 billion candidate row. So I think in both of these, we see that the scalability is actually non-linear. Like in the first one, when we move from 70 million to 700 million, which is a 10x increase, the time actually increased by, I think, around 3.1x only. So that's a sublinear increase in time taken. The second one, which is the deep 1B use case, where I think we have build plus search, which is completing under 2 minutes, and the recall is around 96%. The rabbit queue, which Zhichen talked about, that achieves the same wall clock time, but at a 25x lesser memory. So, which basically shows that the compression is coming effectively for free here. Yep. Moving to 4 real workloads and 3 different modalities. I think the first one, which we are the most proud about, is the entity matching at 2 million queries against a 2 billion candidate. This used to time out earlier, even when we sampled it down to 0.5%, but now it completes within an hour. The W2 through W4 shows a 3 to 10x speed up at 95 to 99% recall. So moving to a practical question which comes on whether we want to have pre-built indexes or build indexes on the fly. So pre-built indexes are generally faster if you have repeatable queries. So it's like 1.7 to 2x faster. But for on-the-fly data exploration, it's actually better to build the indexes on the fly. So our recommendation is use pre-built indexes if you have a repeatable query, and use on-the-fly indexes for exploration. One of the other surprising finding was when we were doing profiling, we found that 99% of the CPU cycles actually go to cluster assignment routing. Index building and search, it takes less than 1% combined. So that was not something which we had expected. It validates that HNSW routing is a critical optimization lever, and we'll talk about it in the future work also. I think using GPU accelerated routing can improve some of these bottlenecks. So tying it all together, we saw that we have 7,000x less network overhead from codec partitioning. We also are using 25x less memory, given we are using RabbitQ and subclustering. We have full SQL composability. And we have 2 ways of building vector search. It's either the power user experience, which is 68 lines of SQL, or the novice experience, which is 12 or 2 levels of API, basically. Yep. So yeah, I think the key point is that these emerge from one decomposition, and they are not separately engineered features, basically. 3 lessons I think we took away. The first one is that building bottoms up. So prove the primitives work, basically at billion scale, before committing to the syntactic sugar. The second one, which we think about the most, is that the hardest part was realizing that we didn't need a new engine. We spent weeks designing new plan node before realizing that existing UDFs were sufficient for this use case. And the third one is codec quality matters a lot more than index algorithm. So tuning your centroid is the best thing we can do, and the rest will follow. To close, we showed that vector search is a relational algebra. We have zero shuffle execution. We have memory bounded indexing and a two-level API. We have 95 to 99% of recall, 3 to 10x speed up, and 7,000 times less network. The future work will revolve around GPU routing, streaming updates, adaptive index, and multimodal capabilities. And then the deeper lesson I leave here is that we didn't build vector search as a new engine. We discovered that SQL engine already had one, and we kind of built the support inside of it. Yep. And with that, yep. Thank you so much.